Hi, Year 10, and today we're going to start with the last practical of the week, and this is looking at testing different materials for insulators. And in terms of practicality, this is quite a useful experiment. There's lots of applications for it, and it describes materials either good or poor thermal insulators or conductors. All right, so here we go. Testing can be done and supported by the book, and that's page 24, 25. First of all, let's look at thermal conductivity and insulation. So conduction, some key terms for you, is the thermal energy transfer which occurs in solids, where vibrating particles pass on kinetic energy or heat to neighbouring particles, and eventually the results occur as a rise in temperature. The energy always travels from an area of high to low temperature, and insulating materials slow down that rate of energy transfer. And some materials are better insulators than others, and they can test this in a whole variety of applications. So we're going to talk about these, but essentially we need to remember that metals tend to be good conductors, but poor insulators, which means they allow heat to escape, whereas plastics are good insulators, but poor conductors. So, one of the practicals that we need to think about is you may have done it with different rods of material, with Vaseline and drawing pins on, and you might have tested different metals. What we're now going to do is look at some of those materials. So what we have is a large beaker. Inside my large beaker, I have a small beaker, and over the top, I've got a piece of card which is acting as a lid, and we've got a thermometer as well as a stopwatch. Although this does look like a particularly safe experiment, we are going to need eye protection, and we're going to look at some different materials to insulate our beaker. And you need access to hot water. That might be via a kettle, or you might boil it in beakers. Glassware is a risk. Hot water is a risk. So here's some tips on how to manage those risks. I would suggest you write them down. So, again, this is where this term hypothesis comes back in. And you need to find out which material is the best insulated by recording the rate at which the water in the beaker loses thermal energy. And the beaker which retains the most heat energy will have the best insulation. So my hypothesis is that I will think that the best insulating material will be cotton wool, and the worst insulator would be foil. My independent variable is the thing that I'm changing, and that is going to be the type of insulation: bubble wrap, tinfoil, cotton wool. And my dependent variable, the thing that I'm going to measure, and that's going to be the temperature of the water. The control variables, things that we're going to need to keep the same and to ensure our results are comparable, are the size of the beaker, the number of layers or the thickness of the material, the volume of water inside my beaker, and then we've got this lovely video for you to watch demonstrating this practical. So 7 steps. Again, let's think about this. Can you shorten these down? I'm pretty sure you can. Try and shorten those down into at least half the capacity. So we're going to set up our containers. We're going to leave one unwrapped, and wrap the others in different insulating materials. We're going to use elastic bands to hold the material in place, and we're going to try and make different wrappings of roughly the different thickness, of the same thickness, so that we can ensure that if we put foil is significantly thinner than bubble wrap, so we might need to put multiple layers of foil. Okay. We're going to use a measure cylinder to measure out equal amounts of hot water, and we're going to put lids on all the containers and fit the thermometer through the hole in the lid. We're going to start the stopwatch and measure and record the starting temperature of the water. We're then going to record it every 2 minutes and record the results down. And we're going to do this for 20 minutes, which means you should end up with 11 results. There is a real importance for accuracy here, so we need to make sure there's equal volumes of water. I do prefer the word volume, okay, so make sure that we're using that to be measured accurately using your measuring cylinder. And the container needs to have its temperature recorded after the same amount of time interval and every overall period. So there's no point in doing one of them every 5 minutes and some of them at 2 minutes and some of them every 1 minute. You can't compare that way. You need to use the same size intervals if we're going to be accurate. So here is my example data, and you can see here we've simplified it down a bit and measured it over 15 minutes, but we've measured every 5 minutes. You would be expected to calculate the difference. So what you would need to do in order to calculate the change in temperature is you would need to take the finished temperature from the start temperature, and that will give you your change in temp. Should be able to calculate that. Try and sketch this table now and calculate that for yourself. Right, so as we can see, we've got 4 results, and we need to look at the data in the table and for each material calculate the change and which material had the largest change in temperature. So be careful here because it does say which material. So therefore the one that had the biggest material is aluminium foil. And actually aluminium foil was as good as not having any insulation at all, because aluminium is a really good conductor of heat. So which material had the smallest change in temperature? Cotton wool. I was right. Get in there. Okay. And when I then plot these onto a graph, we would plot all 3 on the same graph. And you notice it's a line graph and it's a line of best fit. And therefore, throwing out whatever maths have said, it is a curve in this case. And the dependent variable always goes along the bottom axis. If I haven't mentioned that before, I'm mentioning it now. So your dependent variable always goes along the x-axis, whereas the independent variable always goes on the y-axis. Okay. And when we can make our conclusion, we can refer back to our hypothesis. Was it correct? Yes, it was correct, because I am awesome. But state your results and talk about the data and back this with scientific reasoning. Okay, so this is my theory. My hypothesis says that the best material was cotton wool and the worst insulator would be foil. I was right. And then I've now used data. Now, what I've done is that cotton wool only lost 16.2, whereas the foil lost 24 degrees C over the 15-minute period. I've made that direct comparison. Foil is made of aluminium, and one of the properties of metals is they are good conductors of electricity. It's like I've got a degree in science, really. I'm just awesome at this. And then I'm going to talk about the particles being tightly packed and the flow of free electrons, allowing energy transfer to be happening rapidly, which makes it a very poor insulating material. Then I'm going to talk a bit about the fact that cotton wool is not a metal, and they are generally better insulators. There are lots of air spaces and air is known to be a poor conductor of thermal energy. Those air spaces also slow down the rate of energy transfer. There are no free electrons going on. Okay. And then what could have been possible sources of error? Now, if you've done this practical, you get wildly variant results. Okay. And these are the potential reasons. The starting temperature of the water was different in different containers. Again, when you're trying to do this in class, we're all fighting over the kettle, we're all having a chat, not really paying attention. Some people don't wait for the alcohol in the thermometer to go right to the top before they take that initial temperature. So what actually happens is they get a temperature increase, and that's not right, is it? So the temperatures measured slightly different times, and it was difficult to do them all at the same time. Or the insulators have very different thicknesses, and that's, again, really difficult to measure properly. What could have been the possible sources of error? I'm not sure why we got that heading twice, but we could resolve those issues by using an electronic temperature probe or a data logger. We could test different materials at separate times, so different temperature measurement can be more closely controlled. And this is how this is all linked to the specification, just in case you were wondering what exactly are we doing and why. The practical demonstrating the video demonstrating this practical can be found here on YouTube. And I think that's all you really need to know for this one. Yeah, okay. All right then, see you tomorrow, guys. Bye.